Why does everything in the universe spin? Not just planets, not just stars, but everything. From the smallest structures we can observe to the largest cosmic systems ever measured. And more importantly, why has no one ever given you a simple, clear answer that actually feels complete? Because if you think about it carefully, this isn't a small question. It's a deeply uncomfortable one. If spin is everywhere, then it shouldn't be treated as a coincidence. It shouldn't be explained as a side effect. It should have a cause that is just as universal as the phenomenon itself. And yet, most explanations stop too early, telling you that objects spin because of collisions, or because of gravity, or because of how they formed, without ever answering the deeper question. Why does rotation appear in the first place, even before planets exist, even before stars are born? Right now, as you listen to this, you are part of that mystery. You are sitting on a rotating planet that completes a full spin in just under 24 hours. At the equator, that motion reaches about 1,670 kilometers per hour. You don't feel it. You don't notice it. But it's happening. At the same time, Earth is orbiting the Sun at about 30 kilometers per second, while the Sun itself is orbiting the center of the Milky Way, and the galaxy is part of an even larger structure. Everywhere you look, motion curves, motion bends, motion becomes rotation, and the question quietly builds in the background. Why doesn't motion stay straight? Why does it almost always turn into spin? This is where the real story begins. And it's not about distant galaxies or abstract equations. And it's about something much closer to your everyday experience. Imagine throwing a ball. It seems simple. You apply a force, the ball moves forward, gravity pulls it down, and it follows a curved path. That part is familiar, but something else happens every single time. Something so consistent that it almost becomes invisible. The ball spins, always. No matter how carefully you try, you cannot throw a perfectly non-rotating object in real conditions. Your fingers apply slightly uneven forces, and the surface isn't perfectly smooth. The air doesn't flow symmetrically around it. Tiny imperfections create off-center forces, and those off-center forces generate rotation. Now take that idea and expand it far beyond a single object. Imagine not a ball, but an entire cloud of gas and dust stretching across light years, unlike the ones that form stars and planets. These clouds are not perfectly still. They are not perfectly uniform. Observations of molecular clouds in our galaxy show turbulent motions, with different regions moving at different velocities, often influenced by nearby stellar winds, supernova shockwaves, and gravitational interactions. Even slight velocity differences across a cloud introduce angular momentum. And once that angular momentum exists, something remarkable happens. It doesn't vanish. It cannot vanish. This is where you begin to see why this video matters. Because the answer to why everything spins is not hidden in one specific object or one specific event. It's hidden in a principle so fundamental that it governs everything you're about to hear. The conservation of angular momentum. In physics, conservation laws are not optional. They are not suggestions. They are consequences of symmetry. And in this case, the symmetry is rotational symmetry. The idea that the laws of physics do not change if you rotate your point of view. From that symmetry comes a rule. Angular momentum must be conserved in a closed system. That means once rotation exists, even in the smallest amount, it will persist, evolve, and redistribute, but it will not disappear. So here's the reason you should keep listening, because over the course of this journey, you are going to see how that single principle explains the rotation of Earth, the formation of planetary systems, the structure of galaxies, the behavior of black holes, and even the quantum property we call spin. You're going to see how tiny irregularities in the early universe, fluctuations measured in the cosmic microwave background at levels of 1 part in 100,000, eventually led to the vast rotating structures we observe today. And once you understand that connection, everything you thought was separate begins to feel unified. If you find yourself drawn into this kind of quiet exploration, you can take a moment to like the video. Not because it changes what you're about to learn, but because it helps this kind of calm, thoughtful content reach others who might be searching for the same sense of understanding, the same quiet clarity that comes from seeing how the universe actually works beneath the surface. Because the truth is, the universe does not spin by accident. It spins because the moment motion becomes imperfect. Rotation is born, and once it exists, the laws of physics ensure it never truly goes away. You might still be wondering, if everything spins, does that mean rotation had a beginning, a specific moment when motion first turned into spin? Or has it always been there, quietly embedded in every movement since the earliest stages of the universe? Because here's where things become even more intriguing. The idea that rotation simply appears later, after stars or planets form, is not quite correct. In reality, rotation begins much earlier, at the exact moment when motion stops being perfectly aligned, and that moment happens almost immediately in any real physical system, no matter how large or small. To understand this, we need to shift our perspective slightly, not outward into galaxies just yet, but inward into the nature of motion itself. Because in physics, it and perfectly straight, perfectly uniform motion across an entire system is something that almost never exists outside of idealized equations. In the real universe, every collection of matter, whether it's a handful of particles or a cloud spanning light years, contains tiny variations, slight differences in velocity, direction, and position. And these differences are not just noise. They are the seeds of rotation. Imagine a vast cloud of gas in space, cold, diffuse, and slowly evolving under gravity, something astronomers call a molecular cloud. Observations from radio telescopes like ALMA show that these clouds are turbulent, meaning different regions within them are constantly moving in slightly different ways. Some parts drifting faster, others slower, some regions compressing while others expand. And this turbulence is not random chaos, and it's structured motion influenced by nearby stellar activity, shockwaves from supernova explosions, and the gravitational pull of surrounding matter. And within that complexity lies something subtle but unavoidable, a mismatch in motion. Now here's the critical point. When motion within a system is not perfectly aligned, meaning forces or velocities do not pass exactly through a common center, those mismatches create what physicists call torque. And torque is what generates rotation, even if that rotation is initially incredibly small, almost undetectable. It exists, And once it exists, it becomes part of the system's angular momentum. And this is where a fundamental law quietly takes control. Because angular momentum, once present, must be conserved, meaning it cannot simply vanish. It can be redistributed. It can change form. It can spread across a system, but it cannot be destroyed. And this is not just an assumption. It is a direct consequence of rotational symmetry, one of the deepest principles in physics, stating that the laws of nature do not prefer one direction over another. And from that symmetry emerges conservation, a rule that governs motion across the entire universe. So when that molecular cloud begins to collapse under gravity, something remarkable happens. As particles move inward, their distances from the center decrease, and according to conservation of angular momentum, when mass moves closer to the axis of rotation, the rotation rate must increase. This is the same effect you see in a spinning figure skater pulling their arms inward and suddenly spinning faster. But now, imagine that happening not with a person, but with an entire region of space spanning trillions of kilometers. As the cloud contracts, its rotation speeds up, not because something is actively spinning it, but because the rotation was already there, hidden in those tiny initial asymmetries. And as gravity pulls matter inward, it amplifies that rotation, concentrating it, making it more organized, more visible, more dominant, until what was once a barely measurable motion becomes a defining characteristic of the system. But something else happens at the same time, something just as important. The collapsing cloud doesn't remain a sphere. Instead, it begins to flatten into a rotating disk. And this is not an accident. It is the natural outcome of the interplay between gravity, rotation, and collisions. Particles moving above or below the central plane collide with others and gradually lose their vertical motion, while motion within the plane of rotation is preserved. And over time, this process creates a thin, spinning disk, what astronomers call a protoplanetary disk, the birthplace of stars and planets. Inside that disk, rotation is no longer a subtle effect. It becomes the organizing force that determines how matter moves, how it clumps together, and eventually how planets form. Collisions between growing bodies are rarely perfectly head-on. Most impacts occur at angles, transferring angular momentum and causing the resulting objects to spin. And over millions of years, these countless interactions build up the rotation we observe in planets like Earth today. So when you ask why Earth spins, the answer is not a single event. It cannot a single cause, but a chain of processes that trace all the way back to the earliest stages of its formation, and even further back to the motion of the cloud that formed the solar system, and even further back to the conditions of the early galaxy, and ultimately to the initial irregularities present in the universe itself. And this is the deeper realization that begins to emerge. Rotation is not something that needs to be added to the universe. It is something that naturally arises whenever motion is imperfect. And because perfect symmetry does not exist in reality, rotation becomes inevitable. And once it appears, the laws of physics ensure it persists, shaping the structure and behavior of everything that follows. So as we continue, we're going to take this idea further, moving from collapsing clouds to fully formed planets, exploring how rotation affects their structure, their stability, and even their ability to support life. And you may start to notice something subtle happening in the way you think about motion, because what once seemed like a simple, everyday concept begins to reveal itself as one of the most powerful organizing principles in the universe, quietly guiding everything from the path of a falling object to the formation of entire worlds. You might be thinking at this point, if rotation begins so early, if it's built into collapsing clouds and amplified by gravity, then why doesn't it eventually slow down and disappear? Why doesn't everything just settle into stillness over time? Because in everyday life, motion fades, spinning tops fall over, wheels lose speed. Everything seems to come to rest eventually. And so why doesn't the universe behave the same way? The answer lies in a quiet but crucial difference between your everyday environment and the vast emptiness of space, a difference that changes everything about how motion evolves over time. On Earth, motion slows down because of friction, air resistance, contact with surfaces, energy being dissipated as heat. These are the forces that quietly drain motion from everyday objects, turning organized movement into microscopic vibrations, into warmth, into randomness. But in space, most of those processes are almost completely absent. There's no air to resist motion, no surface to rub against, no constant drag slowing things down. And because of that, once something starts rotating in space, it can continue for incredibly long periods of time, often billions of years, with very little change. I take Earth as an example, a planet that formed about 4.5 billion years ago through countless collisions of smaller bodies known as planetesimals. Each of those collisions was slightly off-center, transferring angular momentum and contributing to the planet's rotation. And the result of that chaotic process is the steady spin we experience today. One rotation roughly every 24 hours. But here's the key detail, that rotation is not being actively maintained by some ongoing force. It is simply persisting because there is nothing strong enough to stop it quickly. That doesn't mean it never changes. In fact, Earth's rotation is slowly slowing down, but at a rate so small that it becomes almost invisible on human timescales, about 1.7 milliseconds per century, caused primarily by tidal interactions with the moon, where gravitational forces create ocean tides that slightly lag behind the Earth-Moon alignment, generating a torque that gradually transfers angular momentum from Earth's rotation to the Moon's orbit, pushing the Moon farther away while lengthening Earth's day, a delicate exchange that has been measured with laser ranging experiments, reflecting signals off mirrors placed on the Moon's surface. So even here, rotation isn't disappearing, it's being redistributed, shifted from one form to another, from spin to orbit, always conserved, always present, just changing how it expresses itself. And this is a pattern you'll begin to see everywhere. Angular momentum doesn't vanish, it moves, it flows, it reorganizes, but the total remains. Now consider something even more dramatic. A newly formed planet spinning much faster than Earth, perhaps completing a rotation in just a few hours. In such cases, rotation doesn't just affect how long a day lasts. It begins to shape the planet itself, because rotation introduces what we call centrifugal effects, forces that act outward from the axis of rotation, causing the planet to bulge at the equator and flatten at the poles. And this is not theoretical, it's directly observable. Earth itself is not a perfect sphere. It is an oblate spheroid with an equatorial radius about 21 kilometers larger than its polar radius. And for faster spinning planets like Jupiter, this effect becomes far more pronounced. Jupiter rotates once every 10 hours, despite being more than 11 times wider than Earth. And that rapid rotation causes a noticeable flattening, giving the planet a slightly squashed appearance. And this rotation also drives powerful atmospheric dynamics, creating jet streams, storms, and the iconic banded structure we observe, including the Great Red Spot, a Vishal storm system that has persisted for centuries, powered in part by the planet's rotation and internal heat. So rotation is not just about motion, it becomes a shaping force, influencing structure, behavior, and even long-term stability. And if you imagine removing rotation entirely from a planetary system, the consequences would be extreme. Planets would no longer orbit stably in the same way. Atmospheric circulation would collapse into simpler, less dynamic patterns. Magnetic fields generated by rotating conductive cores might disappear, leaving planets vulnerable to stellar radiation. And over time, the entire architecture of the system would begin to change. And this is why rotation is not just common, it is essential. It provides balance, preventing matter from collapsing directly inward under gravity, allowing stable orbits to exist, and creating the conditions necessary for complex systems to emerge, including the one you are part of right now. If rotation shapes planets and keeps their motion alive across billions of years, then the next question becomes even more important. What exactly is it doing behind the scenes that makes systems stable instead of chaotic? Because at first glance, gravity alone seems enough to explain everything. It pulls matter together, it forms stars and planets, it governs orbits. But gravity by itself has a tendency toward collapse, toward drawing everything inward. And without something to counterbalance that pull, these structures would not last long in their current form. This is where rotation reveals its deeper role, not as a competing force, but as a balancing mechanism, a way for motion to redirect inward collapse into sideways movement, creating orbits instead of impacts, stability instead of destruction. And you can see this most clearly in something as simple as an orbiting object, whether it's the moon around Earth or Earth around the sun. What keeps these bodies from falling straight inward is not the absence of gravity, but the presence of angular momentum. Their sideways motion combined with gravity creates a continuous fall that never quite reaches the center. In more precise terms, an orbit is the result of an object moving forward fast enough that as it falls toward another object under gravity, the surface curves away beneath it, creating a path that loops around instead of ending in collision. And that forward motion, that sideways velocity, is directly tied to angular momentum. Without it, the object would simply fall straight in, and the system would collapse into a single point. This principle extends far beyond simple orbits, shaping entire planetary systems. Stars form at the centers of rotating disks. Planets emerge within those disks, inheriting their motion. And because most of the material shares a common rotational direction, the system becomes organized, coherent, stable over long timescales. And this is not unique to our solar system. Observations of exoplanetary systems reveal similar disk structures, similar rotational patterns, suggesting that this is a universal process. But rotation doesn't just stabilize orbits, it also stabilizes internal processes. Inside planets like Earth, the rotation of the planet contributes to the behavior of its molten outer core, where convection currents of liquid iron generate electric currents, and those currents produce a magnetic field through a process known as the geodynamo. And this magnetic field extends far into space, forming a protective shield that deflects charged particles from the solar wind, preventing the atmosphere from being gradually stripped away. Without rotation, this dynamo process would weaken or fail entirely, and we have a clear example of this in Mars, a planet that once had a stronger magnetic field but lost it as its internal activity declined, leaving its atmosphere exposed to solar radiation, resulting in the thin, cold environment we observe today. And while many factors contributed to that transformation, the loss of sustained internal motion and rotation-driven processes played a critical role. Rotation also affects atmospheres in another way, through the Coriolis effect, which causes moving air masses to curve rather than travel in straight lines, shaping global wind patterns, ocean currents, and large-scale weather systems, including hurricanes and cyclones. And this curvature arises because different parts of a rotating planet move at different velocities depending on latitude, creating subtle but powerful deflections that organize atmospheric motion into complex, dynamic structures. So when you look at a rotating planet, you are not just seeing an object spinning in space. You are seeing a system held in balance, where gravity pulls inward, rotation redirects motion sideways, internal processes generate magnetic fields, and atmospheric dynamics create the conditions necessary for climate and, potentially, life. And all of this emerges from the same fundamental principle, the conservation of angular momentum. And as we continue, we'll move beyond planets to something even larger, systems where rotation doesn't just stabilize individual worlds, but entire galaxies, revealing that the same principle guiding a falling object or a spinning planet also governs structures spanning hundreds of thousands of light years, connecting the smallest motions to the largest patterns in the universe in ways that are both elegant and deeply inevitable. Now that you've seen how rotation shapes planets and stabilizes entire systems, a deeper question begins to form. What about the stars themselves? The massive engines at the center of these systems, the objects that seem so powerful, so dominant, that they should somehow resist or override this pattern. Do they spin for the same reason, or is something else happening at that scale? Because intuitively, you might expect a star holding more than 99% of the mass of a solar system to control everything, including motion itself. And yet, even stars cannot escape rotation. They inherit it, they amplify it, and over time, they slowly lose it, but never completely. When a star forms, it begins not as a star at all, but as part of a collapsing cloud of gas and dust, the same kind of molecular cloud we discussed earlier. And as that cloud contracts under gravity, its angular momentum becomes concentrated, forcing the central region to spin faster and faster, just like a figure skater pulling in their arms. And as the density increases, temperature rises, eventually reaching the point where nuclear fusion ignites in the core, marking the birth of a star. But by that time, rotation is already deeply embedded in its structure. Young stars, in fact, often rotate extremely fast, some completing a full rotation in just a few hours. Observations of star-forming regions confirm this, showing that newly formed stars frequently have high angular velocities, far greater than older stars like our Sun. And this creates a puzzle, because if angular momentum is conserved and most of the mass collapses into the star, then why isn't the star spinning even faster, perhaps so fast that it tears itself apart? The answer reveals another layer of complexity, because during star formation, not all angular momentum ends up in the star. A significant portion is transferred outward into the surrounding protoplanetary disk, into jets of material ejected from the star's poles, and intermagnetic interactions with the environment. These processes act as channels through which angular momentum is redistributed, allowing the star to form without spinning itself to destruction. And this redistribution is not optional, it is necessary. Without it, many stars might never fully form. Even after formation, stars continue to evolve rotationally. They lose angular momentum over time through a process known as magnetic braking, where charged particles emitted in stellar winds are guided by magnetic field lines, carrying angular momentum away from the star, gradually slowing its rotation. And this is not just theoretical. It has been observed across many stars of different ages, showing a clear pattern. Younger stars spin faster, older stars spin more slowly, and this relationship is so consistent that astronomers use it as a method to estimate stellar ages, a technique known as gyrochronology. Our Sun is a perfect example of this process, currently rotating once every 25 days at its equator. But in its youth, it likely rotated much faster, perhaps completing a rotation in just a few days. And over billions of years, its rotation has slowed due to the continuous loss of angular momentum through its solar wind, a process still happening right now. Even as you listen, the Sun is gradually shedding rotational energy into space. But here's where things become even more fascinating, because stars are not solid objects, and they are massive spheres of plasma, and that means they don't rotate uniformly. Different parts of a star can rotate at different speeds, a phenomenon known as differential rotation. In the Sun, the equator rotates faster than the poles, with a difference of several days in rotation period. And this differential motion plays a crucial role in generating the Sun's magnetic field through a process called the solar dynamo. The magnetic field is not static. It evolves, twists, and reorganizes over time, leading to phenomena such as sunspots, solar flares, and the approximately 11-year solar cycle, all of which are directly linked to the interaction between rotation and plasma motion inside the star. So once again, rotation is not just a passive property. It is actively shaping the behavior of the system, influencing energy transfer, magnetic activity, and the star's interaction with its surrounding environment. And just like with planets, if you imagine removing rotation from a star, the consequences would be profound. The internal dynamics would change. Magnetic fields might weaken or disappear. Stellar winds would behave differently. And the entire system, including any orbiting planets, would evolve in a very different way, because rotation is not just part of the star. It is part of the system the star creates. So now, as we continue to expand outward, you begin to see a pattern forming more clearly. Rotation is not limited to specific objects. It is not confined to certain scales. It appears wherever matter moves, wherever asymmetry exists, wherever angular momentum can arise and persist. And the next step in this journey takes us to something even larger. Structures so vast that they redefine what we mean by motion itself. Entire galaxies spinning across hundreds of thousands of light years, carrying this same principle into the largest visible structures in the universe. If planets spin and stars spin, then galaxies, collections of hundreds of billions of stars, must follow the same rule. But here, the scale changes everything, because when you look at a galaxy, you are no longer observing a single object, but a vast rotating system where gravity, motion, and invisible matter all interact in ways that challenge our understanding. And yet, even at this enormous scale, rotation is still there, still persistent, still governed by the same fundamental principle. The Milky Way, the galaxy you are part of, is a rotating disk of stars, gas, and dust, about 100,000 light years across, and the Sun, along with the entire solar system, is orbiting the galactic center at roughly 220 kilometers per second, taking about 225 million years to complete a single orbit, a period sometimes called a cosmic year, meaning that since the Sun formed about 4.6 billion years ago, it has completed only about 20 such orbits. But galaxies do not rotate like solid objects. They exhibit complex rotational behavior, where different regions move at different speeds, influenced by the distribution of mass. And this leads to one of the most important discoveries in modern astrophysics: the study of galaxy rotation curves, which plot how orbital velocity changes with distance from the center. And what scientists found was unexpected, and instead of slowing down at larger distances as predicted by visible matter alone, stars in the outer regions of galaxies continue to move at nearly constant speeds. This observation cannot be explained by the mass we can see. It implies the presence of additional, unseen mass, something we now call dark matter, which appears to make up about 85% of the matter in the universe, and it forms a halo around galaxies, providing the extra gravitational pull needed to maintain these flat rotation curves. So in a very real sense, the way galaxies spin is one of the strongest pieces of evidence we have for the existence of dark matter. But beyond revealing hidden mass, galactic rotation also explains the structure we observe. The spiral arms of galaxies are not fixed objects. They are density waves, regions where stars and gas temporarily cluster together as they orbit the center, much like traffic patterns on a highway where cars move in and out of slow-moving regions. But the overall pattern persists, and this dynamic structure is maintained by the interplay between gravity and rotation. Without rotation, these structures would collapse or disperse, losing their coherence over time. Galaxies themselves formed from the collapse of matter in the early universe, where slight density variations, seeded by quantum fluctuations shortly after the Big Bang, grew under gravity, pulling matter inward. And as with smaller systems, these collapsing regions contain tiny differences in motion, leading to angular momentum. And as they contracted, that angular momentum was amplified, creating rotating disks of stars and gas and the ancestors of modern galaxies. But not all galaxies are neat, rotating spirals. Some are elliptical, with stars moving in more random orbits, and these often form through mergers, when two galaxies collide and their organized rotation is disrupted, scattering stars into new trajectories, redistributing angular momentum across many directions. And while the total angular momentum is still conserved, it is no longer organized into a single coherent rotation, showing that while rotation is fundamental, its structure can be reshaped by large-scale interactions. So when you look at a galaxy, you are not just seeing a collection of stars, you are seeing the outcome of billions of years of motion, collapse, interaction, and conservation, all guided by the same principle that caused a simple object to spin when it was thrown. And this is where the scale becomes almost overwhelming, because the same rule applies everywhere, from the smallest motions to the largest structures we can observe. And as we move forward, we will push this idea even further, beyond galaxies, beyond clusters, toward the possibility that rotation might exist at even larger scales, and toward objects where rotation doesn't just shape matter, but space and time itself. Black holes, where the fabric of reality is pulled into motion in ways that challenge even our deepest intuitions about the universe. At this point, you might feel like you understand rotation as motion, as something objects do, something matter carries and preserves. But what if rotation is not just about objects moving through space? What if rotation actually changes space itself? Because as we move into the most extreme environments in the universe, the familiar idea of spinning objects begins to transform into something far stranger, something where motion is no longer just happening inside space, but is shaping the structure of space-time itself. To see this, we need to look at one of the most extreme objects known in physics: black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. And while black holes are often imagined as simple static objects, the reality is very different. Almost all black holes are rotating, and that rotation introduces effects that have no counterpart in everyday experience. When a massive star collapses at the end of its life, its core shrinks dramatically, from a size comparable to a planet down to something just a few kilometers across. And if that core had even a small amount of rotation before collapse, conservation of angular momentum forces it to spin much faster as it contracts, just like a skater pulling in their arms, but taken to an extreme. And the result is a rotating black hole, described by what physicists call the Kerr solution to Einstein's equations of general relativity. Now here's where things become almost impossible to visualize intuitively. A rotating black hole doesn't just sit there spinning. It drags the very fabric of space-time around with it, an effect known as frame dragging. And in the region surrounding the black hole, called the ergosphere, this dragging becomes so strong that nothing can remain stationary relative to distant space. Everything is forced to move in the direction of the black hole's rotation. Even light itself is compelled to follow this twisting motion. This is not a force in the usual sense. Nothing is pushing objects sideways. Instead, the geometry of space-time has changed. The definition of not moving is altered, and objects follow paths determined by this curved, rotating geometry. So, in a very real sense, the black hole is not just spinning in space, it is spinning space. And this effect is not limited to black holes. It exists wherever there is mass and rotation. Even Earth produces a tiny amount of frame dragging, measured by experiments like Gravity Probe B, which detected minute shifts in the orientation of gyroscopes orbiting the planet, confirming predictions of general relativity with remarkable precision. Though the effect here is incredibly small compared to what happens near a black hole. But near a rapidly rotating black hole, frame dragging becomes dominant. It shapes the motion of matter in the accretion disk, a swirling structure of gas and dust spiraling inward, heating up through friction to millions of degrees and emitting intense radiation. And the closer the material gets to the event horizon, the more strongly it is influenced by the black hole's rotation, allowing matter to orbit at distances that would be impossible around a non-rotating black hole. Even more astonishing, rotation makes it theoretically possible to extract energy from a black hole through a process known as the Penrose process, where particles entering the ergosphere can with one part falling into the black hole and the other escaping with more energy than the original particle, effectively drawing energy from the black hole's rotation, slowing it down ever so slightly in the process. And on even larger scales, this rotational energy may power some of the most energetic phenomena in the universe. Relativistic jets, narrow beams of particles and radiation launched from the poles of accreting black holes, extending for millions of light years into intergalactic space, driven by interactions between rotation, magnetic fields, and space-time curvature, shaping entire galaxies and influencing their evolution over billions of years. So now, the idea of rotation has expanded beyond simple motion, beyond planets and stars, into something that interacts directly with the structure of reality itself, showing that angular momentum is not just conserved, it is deeply woven into the geometry of the universe, affecting not only how matter moves, but how space and time behave. And as we continue, we're going to move in the opposite direction, away from the largest scales and into the smallest, into the quantum world, where rotation takes on a completely different meaning, one that seems disconnected from classical motion, yet remains fundamentally tied to the same principle, revealing that even at the smaller scales, the universe cannot escape the presence of spin. After seeing rotation shape planets, stars, galaxies, and even space-time itself, you might expect that as we move to smaller scales, the concept would simply fade away. That rotation would stop being relevant once we reach the level of atoms and particles. But what actually happens is far more surprising, because at the quantum level, rotation doesn't disappear. It becomes stranger, more abstract, and yet somehow even more fundamental. In classical physics, when we talk about spin, we imagine an object physically rotating, like a planet turning on its axis or a wheel spinning around its center. But in quantum mechanics, particles, such as electrons, possess a property called spin that does not correspond to literal rotation in space. An electron is considered a point-like particle with no measurable size, so there is nothing physically rotating in the classical sense, and yet it carries angular momentum, intrinsic angular momentum that behaves mathematically in ways similar to rotation. This quantum spin is quantized, meaning it can only take on specific discrete values. For an electron, the spin is always 1/2 in units of the reduced Planck constant, and when you measure it along any chosen axis, you will find it in one of two states, often described as spin up or spin down. And this binary nature has profound consequences for the structure of matter. One of the most important principles arising from quantum spin is the Pauli exclusion principle, which states that no two identical fermions, such as electrons, can occupy the same quantum state simultaneously. And this is the reason electrons arrange themselves in distinct shells around atomic nuclei, rather than collapsing into a single lowest energy state. And without this principle, atoms as we know them would not exist. Chemistry would be fundamentally different, and complex structures, including life, might never form. So even though quantum spin is not literal rotation, it still represents angular momentum. It still follows conservation laws, and it still plays a crucial role in determining how matter behaves, showing that the concept of spin extends all the way down to the smallest scales, connecting quantum mechanics with classical physics through a shared underlying principle. Photons, the particles of light, also have spin, but in a different way. They have a spin of 1, and this property is directly related to the polarization of light, the orientation of its oscillating electric and magnetic fields. And when light interacts with matter or passes through certain materials, its polarization can change, revealing information about the structures it has encountered, including the presence of magnetic fields and rotational motion in distant astrophysical objects. So once again, rotation, or at least its mathematical equivalent, appears even where it seems impossible, even where there is no physical object to spin, suggesting that angular momentum is not just a property of objects, but a fundamental feature of the universe itself, embedded in the behavior of particles, fields, and interactions at the deepest level. And this leads to a profound realization. The same principle that causes a ball to spin when you throw it, the same conservation law that shapes planets and galaxies, is also present in the quantum world, governing the behavior of particles and the structure of matter, linking the smallest scales to the largest in a continuous chain of physical law. As we move forward, we're going to bring all of these ideas together, exploring how rotation emerged in the earliest moments of the universe, how tiny fluctuations grew into the vast spinning structures we see today, and whether the universe itself might possess a form of rotation on scales beyond what we can currently observe, pushing the boundaries of what we know and what we can imagine. If rotation appears everywhere, from planets to particles, then a deeper and more unsettling question begins to emerge. Where did the very first spin come from? Because if angular momentum is conserved, it cannot simply appear out of nothing. And yet, the early universe is often described as almost perfectly uniform, almost perfectly symmetrical. So how do you go from that near-perfect symmetry to a universe filled with rotating structures at every scale? To answer this, we need to travel back as far as our current understanding allows, to the earliest moments after the Big Bang, when the universe was extremely hot, dense, and rapidly expanding, and at that time, matter was distributed almost evenly across space, but not perfectly. Never perfectly, because quantum mechanics does not allow perfect uniformity. Even in the most ideal conditions, there are always fluctuations, tiny variations in density and motion that arise from the uncertainty inherent in quantum fields. These fluctuations were incredibly small, differences of about 1 part in 100,000, but they were enough, because gravity amplifies differences. Regions that were slightly denser began to attract more matter, growing over time, while less dense regions became emptier. And as matter flowed into these growing structures, it did not move in perfectly straight, perfectly aligned paths. Instead, there were slight differences in velocity, direction, and timing, and those differences created angular momentum. This is the key idea. Rotation did not need to be created in a single event. It emerged naturally from the imperfections that were already present. And because those imperfections were unavoidable, rotation became unavoidable as well. And as the universe expanded and structures formed, that initial angular momentum was redistributed and amplified, shaping the formation of galaxies, stars, and planetary systems. Cosmological simulations, using our best models of physics and initial conditions measured from the cosmic microwave background, show this process in remarkable detail, starting from nearly uniform distributions of matter. These simulations produce filamentary structures, clusters of galaxies, and rotating systems that closely match what we observe in the real universe, suggesting that the origin of rotation is deeply tied to the initial conditions of cosmic evolution. But here's where things become even more fascinating, because while we can trace the emergence of rotation to these early fluctuations, we still do not have a complete answer to why those fluctuations existed in the form they did, or why they led to the specific distribution of angular momentum we observe today. And this brings us to the edge of current knowledge, where physics meets philosophy, where questions about the origin of motion become questions about the origin of the universe itself. Some theories suggest that during a period known as cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang, quantum fluctuations were stretched to cosmic scales, becoming the seeds of all structure, including the tiny velocity differences that eventually led to rotation. And if this is correct, then the spin of galaxies today is, in a very real sense, a magnified echo of quantum processes that occurred in the earliest moments of existence. So when you look at a rotating galaxy, or even when you feel the passage of day and night caused by Earth's spin, you are experiencing the outcome of processes that began billions of years ago, processes that transformed microscopic fluctuations into macroscopic motion, connecting the smallest scales of physics to the largest structures in the universe. And yet, even with this understanding, one question remains open. Could the universe itself be rotating? Not just the structures within it, but space-time on the largest possible scale. A question that leads us into one of the most speculative and intriguing areas of modern cosmology. After following rotation from quantum fluctuations to galaxies, it's natural to ask, does this pattern continue all the way up? Does the universe itself spin as a whole? Not just its contents, but the fabric of space-time on the largest scale we can imagine. Because if rotation is so fundamental, if it appears everywhere else, then it seems almost inevitable that it might exist at the cosmic level as well. Interestingly, the equations of general relativity do allow for solutions in which the entire universe rotates, one of the most famous being the Gödel universe, proposed in 1949, which describes a rotating spacetime with unusual properties, including the possibility of closed time-like curves, paths through spacetime that could, in theory, allow for travel into the past, creating scenarios that challenge our understanding of causality itself. However, while such solutions are mathematically valid, the real question is whether our universe behaves this way. And to answer that, scientists turn to observations, particularly of the cosmic microwave background, the faint afterglow of the Big Bang, which provides a snapshot of the universe when it was just 380,000 years old. And remarkably, this radiation is extremely uniform in all directions, with only tiny variations that match the predictions of quantum fluctuations, but show no clear evidence of large-scale rotation. If the universe were rotating significantly, and we would expect to see anisotropies, differences in temperature or structure depending on direction, indicating a preferred axis of rotation, but current measurements from missions like Planck and WMAP show no such large-scale pattern, suggesting that if the universe does rotate, it does so at a rate so small that it is effectively undetectable with current technology. But there is an important limitation here. We can only observe the portion of the universe within our observable horizon, about 93 billion light-years across. And beyond that, we have no direct information. So it remains possible, at least in principle, that on scales far larger than we can see, there could be a subtle rotation that we simply cannot detect from our limited vantage point. Some theoretical models explore this possibility, proposing universes with extremely slow rotation, with periods far longer than the age of the universe itself, making the effect practically invisible on observable scales, while others argue that cosmic inflation would have smoothed out any initial rotation, leaving the universe effectively non-rotating at large scales. And at present, there is no definitive answer, only constraints based on what we can measure. So for now, the best conclusion we can draw is that while rotation is fundamental to the structures within the universe as a whole appears, to a very high degree of precision, to be isotropic and non-rotating, at least within the limits of our observations. And this distinction is important because it suggests that rotation arises not from a global property of the universe, but from local processes, from the amplification of small asymmetries as structures form and evolve. And this brings us back to a central idea. Rotation does not need to be imposed from the outside. It does not require a universal spin to explain why galaxies and planets rotate. It emerges naturally, wherever motion is imperfect, wherever symmetry is slightly broken. And because those conditions exist everywhere, rotation becomes a universal feature of the cosmos. As we continue, we're going to explore what would happen if this fundamental property was suddenly removed, if rotation simply vanished, not gradually, but instantly, and how that thought experiment reveals just how deeply rotation is tied to the stability and structure of everything you know. Now imagine something almost impossible, not just unlikely, but fundamentally unnatural. What if, and in a single moment, rotation disappeared, not slowed down, not gradually reduced, but completely removed from the universe? What would actually happen? Because at first, it might seem like a harmless change, perhaps even a simplification. Things would stop spinning, motion would become more straightforward, more predictable. But in reality, the consequences would be immediate, violent, and deeply destabilizing, revealing just how essential rotation is to the structure of everything around you. Start with something familiar: Earth, a planet you experience every day without ever feeling its motion. If Earth suddenly stopped rotating, everything on its surface would continue moving at its original speed due to inertia. At the equator, that's over 1,600 kilometers per hour, meaning oceans, atmosphere, buildings, and everything not anchored to the bedrock would surge eastward at incredible speed, creating global-scale destruction, winds far beyond hurricane strength, massive ocean displacement, and an immediate breakdown of the systems that keep the environment stable. But even if you imagine a scenario where everything somehow stops together, avoiding that initial catastrophe, the long-term effects would still be profound. One side of Earth would face the sun continuously, heating up to extreme temperatures, while the other side would remain in perpetual darkness, cooling dramatically. And between them, a narrow band of twilight would become the only region with moderate conditions, a thin ring where life might persist. But under completely different environmental dynamics than those we know today. The atmosphere would begin to reorganize with heat from the day side flowing toward the night side, creating constant planet-wide circulation patterns. And without the Coriolis effect, weather systems would lose their familiar rotational structure. No hurricanes, no jet streams, just large-scale flows driven purely by temperature differences, fundamentally altering the climate. And then there's something less obvious, but perhaps even more critical: Earth's magnetic field, generated by the motion of conductive material in its outer core, would weaken or disappear because the geodynamo relies on both convection and rotation, and without rotation, the delicate balance required to sustain the magnetic field would break down, leaving the atmosphere exposed to the solar wind, which over long timescales could strip it away, much like what happened on Mars. Now expand that thought experiment outward. Imagine the sun without rotation. Its magnetic field would collapse, the solar dynamo would cease, solar activity would change dramatically, affecting everything from radiation levels to the behavior of the solar wind. And while the sun would still produce energy through nuclear fusion, the way that energy interacts with surrounding space would be fundamentally different. Then consider galaxies, vast rotating systems held together not just by gravity, but by the balance between inward pull and sideways motion. Remove rotation, and stars would no longer orbit the galactic center in stable paths. Instead, they would begin to fall inward, leading to a gradual collapse of the galaxy's structure, potentially forming a much denser, more compact system, perhaps dominated by a central, massive object that's completely unlike the spiral patterns we observe today. Even on the smallest scales, the absence of angular momentum would have consequences. Quantum systems rely on angular momentum for stability. Electrons occupy orbitals defined in part by their angular momentum states. And while this is governed by quantum mechanics rather than classical rotation, the underlying principle remains: without angular momentum, the structure of matter itself would be fundamentally altered. So what this thought experiment reveals is something subtle but powerful. Rotation is not just a feature layered on top of the universe. It is a structural necessity. It provides balance, stability, and organization across scales, and removing it does not simplify the universe. It destabilizes it, breaking the delicate interplay of forces that allows complex systems to exist. And this brings us back to a deeper understanding. Rotation is not optional. It is required for the kind of universe we observe, a universe with planets, stars, galaxies, and life, all of which depend on the presence and persistence of angular momentum. Now that you've seen what happens when rotation is removed, let's explore the opposite extreme. What happens when rotation becomes incredibly fast, pushing the limits of what matter can withstand? Because in the universe, there are objects that spin so rapidly that they challenge our intuition. Objects where rotation is not just a property, but a defining feature of their existence. Among the most extreme of these are neutron stars, the remnants of massive stars that have undergone supernova explosions, leaving behind a core so dense that protons and electrons have combined to form neutrons, creating an object with a mass greater than the Sun, compressed into a sphere only about 20 kilometers across. And when such an object forms, it inherits the angular momentum of its progenitor star. But because it is now vastly smaller, its rotation rate increases dramatically. Some neutron stars, known as pulsars, rotate hundreds of times per second, with the fastest known spinning at over 700 rotations per second, meaning its surface is moving at a significant fraction of the speed of light. And this rapid rotation generates powerful magnetic fields and beams of radiation that sweep through space like cosmic lighthouses, producing pulses of radio waves detectable from Earth with astonishing precision. And these pulses are so regular that pulsars can serve as natural clocks, in some cases more stable than atomic clocks, allowing scientists to test theories of gravity, detect gravitational waves indirectly, and study the properties of matter under extreme conditions, all because of their rapid and stable rotation. But neutron stars are not the only objects that push the limits of spin. Some stars, particularly massive ones, rotate so quickly that they become significantly flattened, with their equatorial regions bulging outward due to centrifugal effects. In extreme cases, the difference between the equatorial and polar radii can be dramatic, giving the star a shape closer to a flattened disk than a sphere. And then there are black holes, where rotation reaches its ultimate limit, governed by the laws of general relativity. A black hole cannot spin arbitrarily fast. There is a maximum rate, often described in terms of its spin parameter, beyond which the equations no longer describe a physically stable object. And yet, observations suggest that some black holes come very close to this limit, spinning at over 90% of the maximum allowed rate. These rapidly spinning black holes influence their surroundings in profound ways, allowing matter in accretion disks to orbit closer to the event horizon, increasing the efficiency of energy release and powering some of the most luminous phenomena in the universe, including quasars, which can outshine entire galaxies. Even smaller objects, like asteroids, can reach rotation limits. Some spin so fast that they begin to break apart, unable to hold themselves together against the outward forces created by their rotation. And in some cases, this process leads to the formation of binary asteroid systems, where fragments remain gravitationally bound and orbit each other. So across the universe, from the smallest debris to the densest remnants of stars, rotation can reach extremes that test the limits of matter, gravity, and physics itself, showing that angular momentum is not just conserved, but can be concentrated, amplified, and expressed in ways that produce some of the most remarkable objects we can observe. And as we move forward, we'll begin to connect these extremes back to the broader picture, exploring how rotation influences not just individual objects, but entire systems over long periods of time, shaping evolution, structure, and the pathways through which matter and energy flow across the cosmos. By now, rotation might feel permanent, almost unchanging, something that begins early and simply continues forever. But there is a quieter, more subtle truth. Rotation evolves slowly, gently, almost imperceptibly, yet over long periods of time, these changes reshape entire systems, and understanding this gradual transformation reveals something deeper about how angular momentum flows through the universe. Take Earth again, not as a static example, but as a system in motion over millions of years. Its rotation is not constant, even though it feels that way to you. Precise measurements using atomic clocks and astronomical observations show that Earth's day is slowly getting longer, increasing by about 1.7 milliseconds per century. And while that change is tiny, over hundreds of millions of years, it becomes significant. Fossil evidence from coral growth patterns indicates that hundreds of millions of years ago, days were shorter, and there were more days in a year, meaning Earth was spinning faster in the distant past. This gradual slowing is primarily caused by tidal interactions with the Moon, as gravitational forces create bulges in Earth's oceans. These bulges are slightly offset due to Earth's rotation, and the gravitational pull between the Moon and these bulges creates a torque that transfers angular momentum from Earth's rotation to the Moon's orbit, causing the Moon to slowly move farther away from Earth at a rate of about 3.8 centimeters per year, measured using laser reflectors placed on the Moon's surface. So once again, rotation is not being lost, it is being redistributed. Earth spins a little slower, the Moon orbits a little farther, and the total angular momentum of the Earth-Moon system remains constant, just expressed differently. And this kind of exchange happens throughout the universe, wherever gravitational interactions occur over long timescales. Eventually, if this process continues, Earth and the Moon will reach a state known as tidal locking, where Earth's rotation period matches the Moon's orbital period, meaning the same side of Earth would always face the Moon, just as the same side of the Moon already faces Earth today. And while this will take billions of years, it represents a stable endpoint, a configuration where energy has been minimized while angular momentum is conserved. This process is not unique. It is common across the solar system. Many moons are tidally locked to their planets. Mercury is in a spin-orbit resonance with the Sun, rotating 3 times for every 2 orbits, and these configurations emerge naturally from the interplay between gravity, rotation, and energy dissipation over time. Even stars evolve rotationally, as we discussed earlier, losing angular momentum through stellar winds, slowing down as they age. And this slowing affects their magnetic activity, their radiation output, and even the environments of orbiting planets, linking the evolution of rotation to the evolution of entire planetary systems. So rotation is not static, it is dynamic, it changes, it flows, it redistributes, and over vast timescales, these changes shape the history of systems, from the length of a day on a planet to the structure of orbits in a stellar system, all guided by the same underlying principle of conservation. And this leads us to another subtle but powerful idea. Rotation is not just about how fast something spins. It is about how that spin interacts with everything else around it, influencing motion, energy, and structure in ways that are often invisible in the moment, but profound over time. If rotation changes slowly and affects entire systems over time, then one of the most important questions becomes, how does it influence the conditions we experience directly, the environment of a planet, the climate, the patterns of weather, and ultimately the possibility of life? Because while rotation may seem abstract, it plays a critical role in shaping the world you live in, often in ways that are easy to overlook. One of the most immediate effects of Earth's rotation is the cycle of day and night, a fundamental rhythm that influences temperature, biological processes, and the behavior of living organisms. But beyond this simple alternation, rotation drives more complex dynamics through the Coriolis effect, which causes moving air and water to curve rather than travel in straight lines, shaping global wind patterns and ocean currents. This curvature leads to the formation of large-scale atmospheric circulation cells, such as the Hadley, Ferrel, and polar cells, which distribute heat from the equator toward the poles, moderating global temperatures and creating the climate zones we experience. And without rotation, this distribution would be far less organized, leading to more extreme temperature differences and less stable climate patterns. Rotation also enables the formation of weather systems with rotational structure, such as hurricanes and cyclones. See where the Coriolis effect causes air flowing toward low-pressure regions to spiral, creating powerful, organized storms. And while these systems can be destructive, they also play a role in redistributing energy and maintaining the balance of the climate system. Ocean currents, driven by wind and influenced by rotation, transport vast amounts of heat across the planet. Currents like the Gulf Stream carry warm water from the tropics toward higher latitudes, affecting regional climates and making certain areas more habitable than they would otherwise be. And these currents depend on the interaction between rotation, wind patterns, and the shape of continents. Rotation also influences the stability of Earth's axial tilt, which determines the seasons, the presence of the moon, itself a product of rotational dynamics and early collisions, what helps stabilize this tilt, preventing large variations that could lead to extreme climate shifts over long timescales. And this stability has likely been important for the development and persistence of life on Earth. Beyond climate, Rotation contributes to the generation of Earth's magnetic field, as we explored earlier, and this magnetic field protects the atmosphere from solar radiation, helping to preserve the conditions necessary for life, showing once again how rotation connects to habitability in multiple ways. So when you think about rotation, it is not just an abstract concept in physics. It is a fundamental factor in shaping the environment you experience every day, from the length of a day to the patterns of weather, from the stability of the climate to the protection of the atmosphere, all of which depend on the presence and persistence of angular momentum. And as we continue, we will begin to explore even more subtle effects of rotation, including how it influences time itself, how it affects measurements and perception, and how it connects to some of the deepest principles in physics, bringing us closer to a complete understanding of why the universe is filled with motion that never truly stops. You've seen how rotation shapes motion, structure, climate, but there's a deeper layer that is almost impossible to feel directly. Rotation also changes time, not metaphorically, not psychologically, but physically, measurably, in ways predicted by relativity and confirmed by experiments. Because once you move fast enough or exist within a strong gravitational field, time itself no longer flows at the same rate everywhere, and rotation plays a role in that difference. On Earth, this effect is incredibly small, almost invisible to human perception, but with precise instruments, it becomes undeniable. A clock at the equator, where rotational velocity is highest, runs slightly slower than a clock at the poles. The difference is only about tens of nanoseconds per day, but it is real, measurable, and accounted for in systems like GPS, where even tiny timing errors can lead to large positional inaccuracies. This happens because motion affects time. According to Einstein's theory of relativity, the faster you move through space, the slower you move through time relative to a stationary observer. And since rotation means continuous motion, especially at high speeds near the equator, time there passes just a little more slowly than at higher latitudes. But now imagine this effect not on Earth, but on an object rotating much faster, like a neutron star. As we discussed earlier, some neutron stars spin hundreds of times per second, meaning their surfaces move at a significant fraction of the speed of light. In these extreme environments, time dilation becomes much more pronounced. If you could somehow stand on the equator of such a star, time for you would pass noticeably slower compared to someone at the poles. Not just a tiny fraction, but enough to matter in physical processes, enough to influence how we interpret signals from these objects, enough to remind us that rotation is not just about motion through space, but about how space and time themselves are experienced. Even in orbit around Earth, astronauts experience slight differences in time compared to people on the surface due to a combination of gravitational and velocity-based time dilation. And while rotation is only one part of that equation, it contributes to the overall effect, showing once again how deeply motion is connected to the fabric of reality. And then, when we return to rotating black holes, this connection becomes even more extreme. Near the event horizon, especially in rapidly rotating systems, time dilation becomes enormous. To a distant observer, processes near the horizon appear to slow down dramatically, almost freezing in time. While for an object falling inward, time continues normally from its own perspective. So rotation, combined with gravity, creates environments where time is no longer uniform, no longer absolute, but relative, dependent on motion and position, revealing a universe where even something as fundamental as time is influenced by the presence of spin. And this leads to a realization that is both subtle and profound. Rotation is not just a property of objects, it is part of the geometry of reality, influencing how time flows, how motion is measured, and how events unfold across the universe. If rotation can influence time, then it should not be surprising that it also changes something more visible: shape. Because when an object spins, it doesn't remain perfectly round, perfectly symmetrical. Instead, rotation redistributes mass, pushing it outward along the equator and flattening it at the poles, creating shapes that reflect the balance between gravity and motion. You can see this effect even on Earth. Although it appears spherical, precise measurements show that it is slightly flattened, an oblate spheroid with a bulge around the equator caused by its rotation. The difference is about 21 kilometers between the equatorial and polar radii, small compared to Earth size, but significant enough to measure and account for in geophysical models. For faster rotating objects, this effect becomes much more pronounced. Jupiter, for example, rotates once every 10 hours, despite its massive size, and this rapid rotation causes a noticeable flattening, making its equatorial diameter about 7% larger than its polar diameter. When you look at images of Jupiter, you are not seeing a perfect sphere, but a shape molded by its own motion. And for even faster rotating stars, the effect can become extreme. Some stars spin so quickly that they become dramatically flattened, almost like spinning disks rather than spheres, with their equatorial regions extended outward. One well-known example is the star Achernar, which has an equatorial radius significantly larger than its polar radius, showing how rotation can reshape even massive stellar objects. But rotation doesn't just change shape, it also changes internal structure. In rapidly rotating stars, the poles can become hotter and brighter than the equator, a phenomenon known as gravity darkening. This happens because the equatorial regions experience a stronger outward force from rotation, reducing the effective gravity there, while the poles remain more compressed, leading to higher temperatures and brightness. So even within a single object, rotation creates differences, gradients, variations that would not exist otherwise, or showing once again how motion shapes not just where things are, but how they behave internally. Rotation also influences how objects break apart. If something spins too fast, the outward forces can exceed the gravitational or structural forces holding it together, leading to fragmentation. This is observed in asteroids, some of which spin so rapidly that they begin to shed material or even split into multiple pieces, forming binary systems or debris fields. So there is a limit to rotation, a balance between cohesion and motion, beyond which structures cannot remain intact. And this limit depends on the object's mass, composition, and internal strength. And this idea of balance appears again and again. Rotation is not just motion. It is a competing influence against gravity, shaping objects into stable forms, but only within certain limits, beyond which stability breaks down. As we move forward, we'll begin to explore how rotation influences not just individual objects, but interactions between them, how it drives energy transfer, how it shapes collisions, and how it determines the architecture of entire systems, revealing that spin is not just something objects have, but something they exchange, share, and transform over time. At this point, you might be starting to see rotation not as something fixed, but as something that moves, something that flows between objects, quietly passing from one system to another, reshaping motion along the way. And this leads to an important question. How exactly does rotation get transferred? How does one object lose spin while another gains it, as without breaking the rule that angular momentum must always be conserved? Because unlike energy, which can transform into many different forms, angular momentum is more restrictive. It must always be accounted for, always balanced. And yet, in the universe, we constantly observe systems where one object slows down while another speeds up, where motion shifts from spin to orbit, from one body to another. And understanding this process reveals something deeply elegant about how the universe organizes itself. One of the clearest examples of this transfer is the Earth-Moon system, which we briefly explored earlier, but now we can look at it more closely because it shows angular momentum in motion, not disappearing, but changing form. As Earth rotates, it drags its ocean tides slightly ahead of the Moon's position, and the Moon's gravity pulls back on these tidal bulges, creating a torque that slows Earth's rotation while simultaneously accelerating the Moon in its orbit, causing it to move farther away. This is not a loss, it is a trade. Earth gives up a small amount of rotational angular momentum, and the Moon gains orbital angular momentum, and the total remains constant, a perfect balance maintained over billions of years. And this kind of exchange is happening all across the universe, wherever gravitational interactions exist. Another powerful example comes from binary star systems, where two stars orbit each other around a common center of mass, and in some cases, these stars are close enough that material from one star begins to flow toward the other, forming an accretion stream, and this flowing matter carries angular momentum with it, spinning up the receiving star while altering the orbit of the system. In such systems, rotation is constantly being redistributed, mass transfer changes, spin rates, orbital periods evolve, and the entire system can undergo dramatic transformations over time, sometimes leading to explosive events like nova or even supernovae, all driven in part by the movement of angular momentum between objects. Even in planetary systems, this exchange plays a role. When planets migrate within a protoplanetary disk, they interact gravitationally with the surrounding material, creating waves in the disk that carry angular momentum away or toward the planet, causing it to move inward or outward, reshaping the architecture of the system. And this process helps explain why we observe exoplanets in such a wide variety of orbits, some extremely close to their stars, others far beyond what we see in our own solar system. And then there are gravitational assists, used by spacecraft to gain speed by passing close to planets, a technique that relies directly on the transfer of angular momentum. As a spacecraft approaches a planet, it interacts with the planet's motion around the Sun, gaining or losing energy depending on its trajectory, effectively borrowing a tiny amount of angular momentum from the planet's orbit, altering its own path without the need for additional fuel. So rotation is not isolated, it is shared, exchanged, redistributed, connecting objects across space in a network of motion that is constantly evolving. And this reveals something profound. Angular momentum is not just a property of individual systems. It is part of a larger, interconnected dynamic, linking the behavior of objects across vast distances and timescales. And as we continue, we'll explore how this exchange of rotation influences some of the most energetic processes in the universe, where motion is not just transferred, but transformed into radiation, heat, and even the creation of new elements, showing once again how deeply rotation is tied to the flow of energy and matter. If rotation can be transferred between objects, then it can also be converted into other forms of energy. And in the universe, this conversion can reach extraordinary levels, producing some of the most powerful and luminous events we can observe, where angular momentum is not just preserved, but actively reshaped into radiation, motion, and transformation. One of the most dramatic examples of this is found in accretion disks, the swirling structures of gas and dust that form around massive objects like black holes and neutron stars as material falls inward under gravity. It doesn't plunge directly into the center. Instead, it spirals, orbiting at high speeds, and in doing so, it creates friction between layers of material moving at slightly different velocities, and this friction converts kinetic energy into heat. The result is an environment of extreme temperature, where gas can reach millions of degrees, emitting X-rays and other high-energy radiation, making these systems some of the brightest sources in the universe. And the efficiency of this process is remarkable. In some cases, up to 10% or more of the mass energy of the infalling material can be converted into radiation, far more efficient than nuclear fusion in stars. This energy ultimately comes from gravitational potential energy and angular momentum. As material loses angular momentum, it moves inward, releasing energy in the process. And this loss is not random. It is facilitated by turbulence, magnetic fields, and interactions within the disk, all working together to redistribute angular momentum outward, allowing matter to fall inward. In some cases, this process also leads to the formation of jets, narrow beams of particles and radiation launched from the poles of the system at near light speeds, extending for vast distances into space. And these jets are thought to be powered by the rotation of the accretion disk and, in some cases, the rotation of the central object itself, particularly in the case of spinning black holes. Through mechanisms involving magnetic fields, such as the Blandford-Znajek process, rotational energy can be extracted from a black hole and converted into electromagnetic energy, driving jets that can influence entire galaxies, heating surrounding gas, and regulating star formation, showing that rotation at one point in space can affect structures millions of light years away. Rotation also plays a role in explosive events like supernovae, where the collapse of a massive star leads to a rapid increase in rotation speed, amplifying magnetic fields and contributing to the dynamics of the explosion, and in the mergers of neutron stars, where rapidly rotating systems collide, producing gravitational waves and creating heavy elements through processes that depend on the extreme conditions generated by their motion. Even gamma ray bursts in some of the most energetic events observed in the universe are thought to be associated with rapidly rotating systems, where collapsing stars or merging compact objects produce intense, focused bursts of radiation, powered in part by the conversion of rotational energy. So rotation is not just a passive feature, it is an active source of energy, a driver of transformation, a mechanism through which the universe converts motion into light, heat, and matter, shaping the evolution of systems across scales. And as we move forward, we'll begin to step back and look at the broader picture once again, bringing together everything we've explored, from the smallest scales to the largest, to understand why rotation is not just common, but inevitable, a consequence of the fundamental structure of physical law itself. After everything you've seen so far, from spinning planets to rotating galaxies and even twisting spacetime, a deeper pattern begins to emerge. Rotation is not just common, it is inevitable. And to understand why, we need to step away from objects and motion for a moment and look at something more abstract, something more fundamental: symmetry. In physics, symmetry does not mean visual beauty or perfect shapes. It means something far more precise. It means that the laws of physics remain unchanged under certain transformations. And one of the most important of these is rotational symmetry. The idea that the laws of nature do not depend on how you orient yourself in space, that there is no preferred direction, no special axis that the universe favors. This might seem like a simple statement, but it has profound consequences because of a principle known as Noether's theorem, discovered by mathematician M.E. Noether in 1915. Every symmetry in the laws of physics corresponds to a conservation law, and for rotational symmetry, the corresponding conserved quantity is angular momentum. This means that the reason angular momentum is conserved is not arbitrary. It is not an additional rule layered on top of physics. It is a direct consequence of the fact that the universe does not distinguish between different directions. And because of that, once angular momentum exists, it must be preserved. It cannot simply vanish without breaking the underlying symmetry of the laws themselves. And this leads to a powerful realization. Rotation is not something the universe chooses to do. It is something the universe is required to allow, because the structure of physical law demands that angular momentum be conserved, and wherever motion is imperfect, wherever asymmetry exists, rotation naturally emerges as a way of preserving that quantity. So when you see a spinning planet or a rotating galaxy, you are not just observing a Slucce phenomenon, you are seeing a direct manifestation of a fundamental symmetry of the universe, a principle that applies everywhere, at all times, across all scales. This also explains why rotation never truly disappears, even when systems evolve, even when motion changes form. Angular momentum is always accounted for, always balanced, whether it is stored in the spin of an object, the orbit of a system, or even in the distribution of motion across many bodies. And this connection between symmetry and conservation is not limited to rotation. It extends to other fundamental quantities as well. The conservation of energy arises from symmetry in time, the idea that the laws of physics do not change from one moment to the next. And the conservation of linear momentum arises from symmetry in space, the idea that the laws are the same everywhere. So in a very real sense, the persistence of motion and rotation is built into the fabric of reality through these symmetries. So now, the question of why everything spins begins to transform into something deeper. It is no longer just about motion or formation. It is about the underlying structure of the universe, the mathematical framework that governs how everything behaves. And within that framework, rotation is not optional. It is a necessary consequence. And as we continue, we will explore how this necessity shapes the universe as a whole, how rotation enables complexity, stability, and the emergence of structures that would not exist otherwise, bringing us closer to understanding why the universe looks the way it does. If rotation is a consequence of symmetry, and if it is preserved across all scales, then the next question becomes even more important. What role does it play in creating the complexity we observe in the universe? Because without complexity, there would be no planets, no stars, no chemistry, no life. And understanding the role of rotation reveals why the universe is not just active, but structured, organized, and capable of evolving into something rich and intricate. At its core, rotation provides a balance against gravity. Without it, matter would tend to collapse directly inward, forming simpler, denser structures. But with rotation, motion is redirected sideways, creating orbits, disks, and stable configurations that allow matter to spread out, interact, and evolve over time. This is why planetary systems form as disks rather than collapsing into single points, why galaxies maintain their spiral structures instead of becoming dense spheres, and why stars can have stable environments around them where planets can exist. All of these structures depend on the presence of angular momentum to counteract gravitational collapse and create stable, long-lived systems. Rotation also enables diversity because small differences in initial conditions can lead to different outcomes in how angular momentum is distributed, resulting in a wide variety of systems, planets with different rotation rates, and stars with different spin characteristics, galaxies with different shapes, all emerging from the same fundamental processes, but evolving in unique ways. In chemistry, the concept of angular momentum appears in the structure of atoms, where electrons occupy orbitals defined by quantized angular momentum states. And this structure determines how atoms interact, how they form molecules, and ultimately how complex chemical systems arise. So even at the smaller scales, angular momentum plays a role in enabling complexity. In biology, the effects of rotation are more indirect, but still essential. The stability of Earth's climate, the presence of a magnetic field, the cycles of day and night, all of which are influenced by rotation, create the conditions necessary for life to develop and persist, and showing that rotation is not just a physical property, but a factor in the emergence of living systems. Even on the largest scales, rotation contributes to the formation of cosmic structures. Galaxies cluster together, forming networks and filaments, and within these structures, angular momentum influences how matter flows, how galaxies interact, and how energy is distributed, shaping the large-scale architecture of the universe. So rotation is not just a feature of motion. It is a driver of complexity, a mechanism that allows matter to organize into stable, diverse, and evolving systems. And without it, the universe would likely be far simpler, far more uniform, and far less capable of supporting the structures we observe. And this leads to a profound conclusion. The fact that everything spins is not just an interesting detail. It is a fundamental reason why the universe is the way it is, a reason why complexity exists, why structures form, and why the cosmos is not a static, featureless expanse, but a dynamic, evolving system full of motion and possibility. As we move forward, we will begin to bring all of these ideas together, exploring how rotation connects the smallest and largest scales, and how it ultimately shapes the experience of being part of a universe that never truly stands still. At this point, something subtle begins to happen in the way you understand the universe. What once felt like separate ideas, planets spinning, stars rotating, galaxies turning, starts to merge into a single continuous pattern, a kind of hidden thread running through everything. And that thread is angular momentum, quietly linking scales that seem completely unrelated, from the motion of a single particle to the behavior of entire cosmic structures. Because when you step back far enough, rotation stops being something individual objects have and becomes something systems share, something that flows through interactions, something that connects cause and effect across space and time. And this is what makes the universe feel less like a collection of isolated things and more like a deeply interconnected process. Think about this. The rotation of Earth is not just about Earth. It is connected to the formation of the solar system, which is connected to the collapse of a molecular cloud, which is connected to the motion of gas in the galaxy, which is connected to the distribution of matter in the early universe. And all of these layers are linked through the conservation of angular momentum, in meaning that what you experience as day and night is part of a chain of motion that stretches back billions of years. And this connection is not just historical, it is active, ongoing, because angular momentum continues to move between systems, shaping interactions in real time. Stars exchange it with their surroundings. Planets exchange it with moons. Galaxies exchange it through mergers and gravitational interactions. And even at the quantum level, particles interact in ways that conserve angular momentum, maintaining this continuity across all scales. This is why the universe feels dynamic, why it evolves instead of remaining static. Because motion is not isolated, it propagates, it influences neighboring systems. It creates patterns that persist and grow more complex over time. And rotation is one of the most fundamental ways this motion is organized. And once you begin to see this, it becomes almost impossible to ignore, because every spinning object becomes a clue, a piece of a larger puzzle, a reminder that what you are observing is not random, but part of a deeply structured system governed by consistent laws. So when you look at the sky, when you see the slow movement of stars across the night, or the changing position of the moon, or even the rotation of clouds in a storm, you are witnessing the same principle at work, expressed in different forms at different scales, but always following the same underlying rule. And this realization leads to something almost philosophical, because it suggests that the universe is not just filled with motion. It is defined by it, shaped by it, sustained by it. And rotation is one of the clearest expressions of that motion, a visible sign of a deeper, invisible order. And as we continue, we'll begin to explore how this order influences not just physical systems, but perception itself, how rotation affects the way we measure, navigate, and understand the world. bringing the concept even closer to your everyday experience. If rotation is everywhere, shaping the universe from the largest scales to the smallest, then it's not surprising that humans, long before understanding the physics behind it, began to observe, measure, and eventually use rotation as a tool, turning a fundamental property of the cosmos into something practical, something that could guide navigation, timekeeping, and exploration. One of the earliest examples of this is the observation of the night sky, where the apparent rotation of stars around a fixed point provided a reliable reference for direction. Ancient civilizations noticed that certain stars remained nearly fixed in the sky, particularly Polaris in the northern hemisphere, and by tracking the position of stars relative to this point, they could determine direction and navigate across vast distances. This method of navigation relied directly on Earth's rotation, even though the people using it may not have fully understood the underlying mechanics. They were, in effect, using the spin of the planet as a guide, turning a cosmic motion into a practical tool for survival and exploration. As timekeeping developed, rotation became even more central. The cycle of day and night, driven by Earth's spin, provided the most natural unit of time, and early clocks were designed to measure this cycle, eventually leading to more precise instruments that could track smaller intervals, but always anchored to the rotation of the planet. The development of accurate timekeeping, particularly the marine chronometer in the 18th century, allowed sailors to determine longitude by comparing local time to a reference time, effectively using Earth's rotation as a global clock, a method that transformed navigation and made long-distance sea travel far more reliable. In modern technology, rotation continues to play a critical role. Gyroscopes, devices that maintain their orientation due to conservation of angular momentum, are used in everything from aircraft navigation systems to smartphones, allowing devices to detect changes in orientation and motion with remarkable precision. Inertial navigation systems combine gyroscopes with accelerometers to track movement without relying on external references, making them essential for submarines, spacecraft, and other systems where traditional navigation methods are not possible. And once again, these technologies rely on the fundamental property that angular momentum resists change, providing stability and predictability. Even in space exploration, rotation is used strategically. Rockets are launched eastward to take advantage of Earth's rotational speed, gaining an additional boost that reduces fuel requirements, and spacecraft use rotational dynamics to stabilize their orientation and control their movement through space. So what began as a simple observation of the sky has evolved into a deep understanding of rotation as a tool, something that can be measured, predicted, and harnessed, showing that this fundamental property of the universe is not just an abstract concept, but something that directly influences how we interact with the world. And as we move forward, we will begin to explore how rotation influences not just motion and technology, but perception itself, how it shapes the way we experience reality, and how understanding it more deeply can change the way you see the universe, not as something distant, but as something you are constantly moving within. You are moving right now, faster than most airplanes, carried effortlessly by a planet rotating through space, And yet you feel nothing, no wind rushing past you, no sense of motion, no hint that you are traveling at over 1,000 miles per hour if you're near the equator. And that raises a quiet, almost unsettling question. Why don't you feel it? The answer is not that you are still, but that everything around you is moving with you, perfectly, continuously, without interruption. And because of that, your body has no reference point to detect the motion. Motion in itself is not what you feel. What you feel is change in motion, acceleration, differences, shifts. And when movement is constant and shared, it becomes invisible. This is the same reason you don't feel motion on a smooth airplane flight. Once the plane reaches cruising speed, you no longer feel the forward motion, because everything inside the cabin, the air, the seats, your body is moving at the same speed. There is no difference to detect, no signal for your senses to interpret as motion. Earth works the same way, but on a much larger scale. The atmosphere rotates with the planet. The oceans move with it. Even the ground beneath your feet is part of that motion. So from your perspective, everything appears still, even though you are part of an enormous rotating system. But the effects of this rotation are still there, just not in ways you directly feel. You see them in subtle patterns, in the way storms spiral, in the way long-distance flights curve across the globe, in the behavior of ocean currents, all shaped by the Coriolis effect, a consequence of Earth's rotation influencing moving objects. If Earth were to suddenly change its rotation speed, you would feel it immediately, because that would introduce acceleration, a change in motion, and your body would respond. But as long as the rotation is steady, smooth, and shared, it remains hidden in a silent motion that defines your world without announcing itself. And there is something almost calming in that realization, that you are always in motion, always part of a spinning system, yet able to experience stillness, because your frame of reference moves with you. It's a reminder that perception is relative, that what feels stationary is often just motion without contrast. So when you stand still and feel grounded, you are not outside of motion. You are perfectly aligned with it, moving in harmony with a rotating planet, orbiting a rotating star, within a rotating galaxy, all without feeling the need to notice. And as we continue, we'll begin to explore how this hidden motion becomes visible again when systems are pushed out of balance, when rotation interacts with forces in ways that reveal itself dramatically, sometimes violently, reminding us that what is usually invisible can suddenly become undeniable. Most of the time, rotation creates stability, orbits, balance, structure. But under certain conditions, that same rotation can lead to instability, to breakdown, to sudden and sometimes violent change. And understanding this transition reveals something important. Rotation is not inherently stable. It is stable only within limits, because every rotating system exists in a balance between inward forces, like gravity or structural strength, and outward forces created by motion. As long as that balance holds, the system remains stable. But if rotation becomes too fast, or if the structure weakens, that balance can break. And when it does, the results can be dramatic. Take asteroids, for example. To many are loosely bound collections of rock and debris held together by their own gravity. Some of them rotate slowly, completing a full spin over many hours, but others spin much faster And when their rotation rate increases beyond a certain point, the outward forces at their surface exceed the gravitational forces holding them together. When that happens, material begins to drift away, first slowly, then more rapidly, sometimes leading to the formation of a debris cloud or even the breakup of the asteroid into multiple pieces. In some cases, this process creates binary asteroid systems, where two fragments remain gravitationally bound and orbit each other. This increase in rotation can be driven by subtle effects, such as uneven heating from sunlight, known as the Yorp effect, where absorbed and re-emitted radiation creates a tiny but continuous torque, gradually spinning the asteroid faster over time. It's a quiet process, but over thousands or millions of years, it can push the system past its stability limit. On a much larger scale, similar principles apply. Rapidly rotating stars can approach what is known as the breakup velocity, the point at which centrifugal forces at the equator nearly overcome gravity. At this limit, stars can begin to lose mass, shedding material into space, forming disks or streams of gas that carry away angular momentum. Even accretion disks around black holes can become unstable, with turbulence and magnetic interactions creating chaotic flows that redistribute angular momentum in complex ways, and sometimes leading to sudden bursts of energy or changes in brightness that we observe as variability in distant galaxies. So rotation is not just about smooth, continuous motion. It can also be the source of tension within a system, a stored energy that, under the right conditions, can be released, reshaping the structure of the object or system involved. And this dual nature is important. Rotation creates stability, but it also sets limits, boundaries that cannot be crossed without consequence. And when those limits are reached, the system must respond, often in ways that reveal just how much energy and motion had been quietly stored within it. As we move forward, we'll begin to explore how these instabilities connect to larger processes, how they influence formation, destruction, and transformation across the universe, showing once again that rotation is not just a background feature, but an active force shaping the evolution of everything around us. By now, you've seen rotation as something steady, something stabilizing, but also something that can push systems to their limits. And in that tension between balance and instability lies one of the most important roles rotation plays in the universe. It doesn't just maintain structures, it decides how they are born and how they end. Because every time matter gathers under gravity, rotation becomes part of the story. It resists collapse just enough to spread material into disks, to create orbits instead of direct infall, to allow collisions instead of immediate compression. And this slight resistance is what makes formation possible. Think about star formation again, but more slowly this time. A cold cloud of gas begins to collapse under gravity. Without rotation, everything would fall inward along straight paths, compressing into a dense object quickly. But because real clouds are never perfectly still, there is always some angular momentum. And as the cloud contracts, that rotation speeds up, forcing material into a flattened disk. Inside that disk, something remarkable happens. Structure begins to emerge. Instead of a single collapse, you get rings, clumps, instabilities, regions where matter gathers, cools, sticks together. Over time, these become planets. So rotation doesn't just delay collapse, it transforms it into organization. But the same principle also governs destruction. When a massive star reaches the end of its life, its core collapses rapidly, and as it shrinks, its rotation rate increases dramatically, as like a spinning skater pulling in their arms. This amplification of rotation can twist magnetic fields, drive jets, and influence the explosion itself. In some cases, rotation helps trigger asymmetries in supernova explosions, sending material out in preferred directions rather than evenly in all directions. In others, it may prevent a full explosion, allowing the core to collapse directly into a black hole. So, rotation doesn't just shape formation, it shapes endings. It determines whether a star explodes or quietly collapses, whether a system fragments or remains intact, whether matter spreads outward or falls inward. And sometimes, formation and destruction are not separate events, but part of the same process. When galaxies collide, their organized rotation is disrupted. Stars are scattered, orbits change, and gas clouds compress and ignite new waves of star formation. Out of the destruction of order comes a new kind of structure. So, rotation is not just a stabilizing force, it is a creative force, and a destructive one. It decides how matter organizes, how energy is released, how systems evolve over time. And this leads to a deeper realization. The universe is not simply building things or breaking them, it is constantly transforming them. And rotation is one of the key mechanisms that makes that transformation possible. If rotation shapes everything we see today, then the natural question becomes, where did it begin? Not just in stars or galaxies, but at the very start, in the early universe itself. Because right after the Big Bang, the universe was remarkably simple. Hot, dense, almost uniform. Matter and energy spread out rapidly as space expanded, and at first glance, it might seem like there was no room for rotation at all, no large structures, no organized motion. But perfect uniformity is impossible. Even in the earliest moments, there were tiny fluctuations, slight differences in density and velocity arising from quantum effects. These differences were incredibly small, but they mattered. As the universe expanded and cooled, gravity began to amplify these fluctuations. Slightly denser regions pulled in more matter, growing over time. And as matter flowed toward these regions, it didn't fall in perfectly straight. There were always tiny sideways motions, tiny asymmetries, and those asymmetries created angular momentum. So rotation did not need to be added later. It was already there, hidden in the initial conditions, awaiting to be amplified. As these regions collapsed to form the first galaxies, their rotation increased, just like the collapsing solar nebula we discussed earlier. Clouds flattened into disks, stars formed within them, and the large-scale structure of the universe began to take shape. This means that when you look at a rotating galaxy today, you are seeing something that traces back to the earliest moments of cosmic history. Its spin is not random. It is the amplified result of tiny differences present at the beginning. And this raises a deeper question. Was the universe itself rotating? According to current observations, the answer appears to be no, or at least not in any measurable way. The universe looks nearly the same in all directions, with no preferred axis of rotation. Measurements of the cosmic microwave background as the afterglow of the Big Bang show an extraordinary level of uniformity, but there are theoretical models that allow for a rotating universe where space-time itself has a kind of global spin. These models are not supported by current data, but they remind us that rotation is deeply connected to the structure of space-time itself. Even if the universe as a whole is not rotating, the fact that rotation emerges so naturally at smaller scales tells us something important. It tells us that given even the slightest asymmetry, even the smallest fluctuation, rotation will appear. It is not a rare outcome. It is a natural consequence of how matter and motion interact under the laws of physics. So the spin you see everywhere, in planets, stars, galaxies, is not a coincidence. It is the echo of the beginning, a memory of tiny imbalances you stretched and amplified over billions of years. And as we move forward, we'll begin to bring all of these ideas together, not just as separate phenomena, but as parts of a single, unified picture. One where rotation is not just present everywhere, but essential to the very existence of structure in the universe. By now, you can almost feel it. Rotation is not just present, it is shaping entire cosmic structures, and nowhere is this more visible than in galaxies, vast systems of hundreds of billions of stars, all moving in patterns that reveal something deeper than just gravity, something hidden, something we cannot see directly, but can only infer through motion. When astronomers began measuring how fast stars move within galaxies, they expected a familiar pattern, similar to the solar system, where objects farther from the center move more slowly, because most of the mass is concentrated in the middle. But what they found was something completely different. Instead of slowing down, stars far from the center of galaxies move just as fast as those closer in. The rotation curves of galaxies are flat, meaning the orbital speed remains nearly constant across large distances. And this should not be possible if only visible matter were present. Something else must be there, something invisible, providing additional gravitational pull to keep those outer stars moving so fast without flying away. And this is what we call dark matter. So here's the profound part. We didn't discover dark matter by seeing it. We discovered it by watching rotation. By observing how galaxies spin, we realized that most of their mass is not made of stars or gas, but something unseen, making up about 85% of the matter in the universe. Rotation, once again, becomes a tool of revelation. It shows us not just what is there, but what must be there, even if we cannot detect it directly. And this hidden mass doesn't just sit in the center. It forms a halo around galaxies, extending far beyond the visible stars, shaping how galaxies rotate, how they form, and how they interact with each other. Without dark matter, galaxies as we know them could not exist. They would not have enough gravity to hold themselves together at the speeds we observe. And without rotation revealing this discrepancy, we might never have known. So when you look at a spiral galaxy, you are not just seeing a beautiful structure, you are seeing evidence of something deeper, a hidden framework revealed through motion, through spin, through the behavior of stars, tracing out paths shaped by forces we cannot see. And this reminds us again, rotation is not just motion, it is information. It tells us what is present, what is missing, what must exist beyond what we can directly observe. And as we continue, we will move even further outward, exploring how rotation might exist on the larger scales of all, not just within galaxies, but across the vast cosmic web that connects them. As we zoom out further, beyond galaxies, beyond clusters, into the largest structures in the universe, we begin to see a vast network, the cosmic web in an immense structure made of filaments of galaxies stretching across hundreds of millions of light years, separated by enormous voids. At this scale, the universe looks less like isolated systems and more like a connected fabric, threads of matter woven together by gravity, forming nodes where galaxies cluster and long filaments where they align. And here, a new and subtle question emerges. Does rotation exist even at this scale? Do these enormous filaments, spanning distances almost impossible to imagine, also spin? This is not an easy question to answer. The motions involved are incredibly slow, and the distances are so vast that detecting rotation requires extremely precise measurements. But recent observations and simulations have hinted at something intriguing. In some cases, near galaxies along a filament appear to show a slight preference for motion in a particular direction, suggesting that the entire filament might have a small rotational component, like a slow, almost imperceptible twist along its axis. If this is real, it would mean that rotation exists at scales far larger than galaxies, extending across the largest known structures in the universe. It would mean that angular momentum is not just a local property, but something distributed across cosmic distances. The origin of such rotation would likely trace back to the same early fluctuations we discussed before. Tiny differences in velocity in the early universe could have grown over time, not just forming galaxies, but influencing the motion of entire filaments. Computer simulations of cosmic structure formation show that as matter flows along these filaments toward dense regions, it can acquire angular momentum, creating large-scale rotational patterns. But this is still an open question. The evidence is not yet conclusive. Some observations suggest rotation, others do not. It remains an area of active research, a frontier where our understanding is still evolving. And that uncertainty is important. It reminds us that even though we've uncovered so much about rotation, there are still layers we do not fully understand, still patterns we are only beginning to see. But whether or not the cosmic web rotates as a whole, the possibility itself tells us something powerful. That rotation may not have a natural boundary. That given enough scale, enough time, enough interaction, angular momentum can appear almost anywhere. And this brings us closer to a final realization. Rotation is not confined to specific objects or systems. It is a universal tendency, a natural outcome of motion, asymmetry, and conservation, appearing wherever conditions allow it to emerge. As we continue, we'll begin to bring this journey toward a deeper conclusion, connecting everything from the smallest quantum spins to the largest cosmic structures, revealing why rotation is not just everywhere, but unavoidable. At this point, you've traveled across scales, from planets and stars to galaxies and beyond. But now we turn inward again to the smallest building blocks of reality, because something remarkable happens when you look closely enough. Rotation doesn't disappear, it changes form. At the quantum level, our particles do not spin in the way planets or stars do. An electron is not a tiny sphere rotating in space. In fact, as far as we know, it has no size at all. And yet, it still has something we call spin. This spin is not a physical rotation you could watch, but it behaves like angular momentum. It has direction, it can be measured, it follows conservation laws, and it plays a crucial role in how particles interact, how atoms form, and how matter itself is structured. Electrons, for example, have a spin of 1/2 in quantum units, This seemingly abstract property determines how they can occupy space around an atom nucleus. Because of the Pauli exclusion principle, no two electrons with the same spin can occupy the same quantum state. And this is why atoms have structure, why electrons form shells instead of collapsing inward, and why chemistry exists at all. So even at the smallest scale, something like rotation, or at least its mathematical equivalent, is essential for stability and complexity. Without it, matter would not organize the way it does. The periodic table would not exist. Molecules would not form in the same way. Photons, the particles of light, also carry spin. And this spin determines how light is polarized, how it interacts with matter, how it transfers energy. So even something as intangible as light carries this property, linking motion and interaction in subtle ways. And when you step back again, something beautiful emerges. The same concept, angular momentum, appears at every scale, in atoms, in planets, in galaxies. Not identical in form, but consistent in principle. And it is as if the universe is built on a repeating idea, that motion can be organized around an axis, that this motion must be conserved, and that from this simple rule, complexity can arise. So when you think about rotation now, it is no longer just something large and visible. It is something embedded in the structure of reality itself, from the smallest particles to the largest cosmic systems. And this continuity, this repetition across scales, is one of the strongest clues we have that the laws of physics are unified, that the same principles apply everywhere, even when they appear in very different forms. And as we move forward, we will begin to reflect on what this means, not just physically, but conceptually. What it means to exist in a universe where motion never truly stops, where spin is not an exception, but a rule. Now, after everything you've seen, everything you've followed from the smallest quantum properties to the largest cosmic structures, a quiet realization begins to settle in. The universe cannot be still. Not because something is constantly pushing it, not because there is some external force driving motion, but because stillness itself is almost impossible under the laws of physics as we understand them. Perfect stillness would require perfect symmetry. Every particle at rest, every force exactly balanced. No differences in motion, no fluctuations. But quantum mechanics tells us that such perfection cannot exist. There are always tiny variations, always uncertainty, always motion at some level. And once even the smallest motion exists, angular momentum can emerge. And once angular momentum exists, it must be conserved. It cannot simply disappear. It can move, it can transform, it can redistribute, but it remains. So the universe is not just moving by chance. It is moving because it must, because its fundamental laws prevent complete stillness, because symmetry leads to conservation, because conservation preserves motion. And this motion takes many forms: linear motion, rotation, vibration. But rotation stands out because it organizes motion around something, around an axis, around a center, creating patterns that persist, structures that remain stable over time. Without rotation, motion would be more chaotic, more direct, more prone to collapse. But with rotation, motion becomes structured. It becomes cyclical. It creates orbits, disks, systems. It allows complexity to grow instead of being erased. So when you look at the universe now, you are not just seeing movement. You are seeing the impossibility of stillness made visible. Every spinning planet, every rotating star, every galaxy turning slowly over millions of years, they are all expressions of the same truth. That motion is fundamental, that stillness is fragile, and that the universe exists in a state of continuous transformation. And there is something almost calming in that idea, that everything is in motion, yet governed by laws that create balance, that maintain structure, that allow patterns to persist, even as everything changes. So you are not in a quiet, static universe. You are in a moving one, a universe that flows, that spins, that evolves, and that never truly stops. And as we approach the final chapters, we'll begin to bring this journey to a gentle close. Not by ending the motion, but by understanding it more deeply, by seeing how everything you've learned connects back to your own place within this endlessly rotating cosmos. By now, the idea has become almost impossible to ignore. Everything spins, but there is one more step in understanding this truth, realizing that this is not something happening out there in distant galaxies or abstract physics. It includes you. Right now, as you sit or lie still, you are part of multiple layers of motion, all happening at once, all perfectly coordinated, all invisible to your senses. You are rotating with Earth once every day, orbiting the Sun once every year, and moving with the Sun around the center of the Milky Way over hundreds of millions of years. And beyond that, the galaxy itself is moving within a larger structure, drifting through the cosmic web in part of an even greater motion that stretches beyond what we can easily imagine. So your sense of stillness is not the absence of motion, it is alignment with it. You are moving in harmony with everything around you, carried by systems so vast and stable that they feel like rest. Even your body reflects this pattern. On the smallest scales, the atoms that make up your cells are governed by angular momentum. Electrons occupy orbitals shaped by quantum spin. Molecules vibrate and rotate. Processes inside your body depend on structures that exist because angular momentum is conserved. So the same principle that shapes galaxies also shapes you. The same law that governs the spin of a star also governs the structure of the atoms in your body. And this connection is not just poetic, it is physical. It means that you are not separate from the universe's motion. You are a continuation of it, a local expression of the same processes that have been unfolding since the earliest moments of cosmic history. When you breathe, when your heart beats, when your body maintains its structure, it does so within a framework shaped by the same rules that govern everything else. So the next time you think about rotation, it is not something distant or abstract. It is something you are part of, something you are experiencing constantly, even if you never feel it directly. And there is something quietly comforting in that idea, that you are not standing still in a moving universe. You are moving with it, carried by it, part of its continuous flow. And as we move toward the final chapters, we'll begin to bring this understanding into a deeper perspective, not just as a physical truth, but as a way of seeing the universe as a connected, evolving whole. After everything we've explored, from the smallest particles to the largest cosmic structures, from the formation of stars to the motion of galaxies, the question we started with, why does everything spin, begins to feel different. At first, it seemed like a mystery, a pattern that needed an explanation. But now, it feels more like an inevitability. Everything spins because motion is never perfectly balanced, because tiny asymmetries always exist, because once motion appears, angular momentum must be conserved. Everything spins because gravity pulls matter inward, but motion redirects that collapse into orbits and disks. Because energy flows through systems, redistributing motion rather than eliminating it. Everything spins because the laws of physics are symmetric, because they do not prefer one direction over another. And because of that symmetry, angular momentum becomes a quantity that cannot disappear. And everything spins because rotation creates stability. It allows structures to form instead of collapsing. It allows systems to persist instead of dissolving. It allows complexity to emerge instead of being erased. So rotation is not just a feature of the universe, it is a requirement for the kind of universe we live in. Without it, there would be no stable planetary systems, no galaxies with spiral arms, no stars with orbiting worlds, no atoms structured in ways that allow chemistry. The universe would still exist, but it would be simpler, more uniform, less dynamic. It perhaps even incapable of supporting the structures that make life possible. So the reason everything spins is not a single cause, but a combination of deep principles: symmetry, conservation, gravity, and motion, all working together to produce a universe that is not static, but alive with movement. And when you bring all of these ideas together, something quiet but powerful emerges. Rotation is not an accident. It is not a coincidence. It is not a detail. It is a fundamental expression of how reality works. And now, as we move into the final closing, we'll gently step back from the details and allow everything you've learned to settle, not as separate facts, but as a single, coherent understanding of a universe that never truly stands still. At this point, you don't need to analyze anymore. You don't need to track every detail, every mechanism, every equation, because something deeper has already happened. The idea has settled. Everything spins, not as a fact to remember, but as a pattern you now recognize. And as you let that idea rest gently in your mind, you might begin to notice something subtle. The universe no longer feels chaotic or random. It feels structured, rhythmic, almost calm, because rotation is not violent by nature. It is repetitive, cyclical, predictable, a kind of motion that returns to itself again and again. Day becomes night, night becomes day. Orbits repeat, cycles continue. Galaxies turn slowly, almost imperceptibly. There is something deeply steady about that kind of motion. And maybe that's why, even though you are moving through space at incredible speeds, you feel still, because the motion is smooth, continuous, balanced. You are not being thrown through the universe. You are being carried by it, carried by a rotating planet, carried by a star in orbit, carried by a galaxy turning through space. And none of it requires effort from you. None of it asks anything of you. It simply continues. So instead of thinking about motion as something active, something forceful, you can begin to see it as something gentle, something that holds things together rather than pulling them apart. Rotation is not chaos. It is order in motion. And as you let that idea settle, your mind can begin to relax into it. No need to follow every layer. No need to keep track of every scale. Just the quiet understanding that everything is moving and everything is still balanced. Now imagine, not as a thought experiment, but as a feeling that you are drifting, not falling, not rushing, just drifting. Because that is closer to what is actually happening than anything else. You are drifting through space on a rotating world, surrounded by an atmosphere that moves with you. warmed by a star that itself is moving, all of it embedded in a galaxy that turns slowly over time. And beyond that, the universe itself expanding, stretching space, carrying galaxies farther apart, not because they are flying outward, but because the space between them is growing. So motion is not always something that happens through space. Sometimes it is something that happens with space. And within that expansion, within that vast, quiet movement, rotation adds structure. It adds direction. It gives form to motion that would otherwise be too diffuse to notice. It creates spirals instead of randomness, orbits instead of collapse. It patterns instead of noise. So as you drift, you are not lost in motion. You are part of a pattern within it. And there is something deeply calming in that realization that even though the universe is vast, even though everything is moving, that motion is not chaotic. It is guided, shaped, balanced. You are not being carried into the unknown. You are being carried within a system that has been stable for billions of years. A system where motion and structure coexist, where change and stability are not opposites but partners. And as you let your thoughts slow down, you can begin to match that rhythm, not forcing anything, not trying to understand more, just allowing yourself to exist within the same gentle flow, because the universe does not rush, it does not hurry, it spins, it drifts, it continues, and so can you. At this point, as the question has softened, it is no longer why everything spins, but simply the recognition that it does, and that it always has. And when you stop asking and just observe, something changes. The universe begins to feel less like a problem to solve, and more like a rhythm to follow. Because rotation is not just motion, it is repetition, a quiet returning, a cycle that never quite ends, but never feels rushed either. Think about it. Every rotation is a loop, a return to where it began, but not exactly the same. A subtle continuation. Earth turns, and the same horizon comes back. But time has moved forward. The moon orbits, and the same face appears. But the sky has shifted. Galaxies spin, and stars trace paths that repeat over millions of years. But nothing is ever frozen. It is motion, but it is also memory. And there is something deeply calming in that kind of motion, because it is not unpredictable. It is not chaotic. It is steady. Even when systems evolve, even when things change over time, the underlying rhythm remains. Rotation continues. Angular momentum persists. So instead of thinking about the universe as constantly changing, you can begin to feel it as constantly flowing, with patterns that repeat, with structures that hold, with motion that sustains itself. And in that flow, there is no need to hold on tightly to any single moment, because everything returns in some form, not exactly the same, but never entirely lost. Rotation becomes a kind of quiet reassurance that even in motion, there is continuity. And as you sit with that idea, you might begin to feel your own rhythm slowing down, aligning in a small way, kiss with something much larger, something that has been spinning long before you were here and will continue long after. By now, you've explored so much, from quantum spin to galaxies, from gravity to symmetry, and it would be easy to feel like you need to remember it all. But you don't, because understanding the universe doesn't come from holding every detail at once. It comes from allowing the pattern to remain, even as the specifics fade. And the pattern is simple. Motion exists, rotation emerges, angular momentum is conserved. That's it. Everything else, all the examples, all the scales, all the systems, They are just different expressions of that same idea. So there's no need to keep thinking through each layer. No need to replay every explanation. And you can let the details drift away, like objects moving out of focus, while the deeper understanding stays quietly in the background, because the universe does not require you to understand it perfectly in order to be part of it. You are already included, already moving within it, already aligned with its laws, whether you think about them or not. And sometimes, the most peaceful way to understand something is not to hold on to it tightly, but to let it settle, to let it become something you feel rather than something you analyze. So if your thoughts begin to slow, if the details start to blur, that's not a loss. That's the point. Because now, instead of thinking about rotation, you're simply existing within it. There is something you may have noticed, quietly, in the background of everything we've explored. Nothing in the universe feels rushed. Even the fastest rotations, even the most extreme spinning objects exist within systems that unfold over time in ways that are measured, continuous, and balanced. A planet spins once every day. A star rotates over weeks. A galaxy turns over hundreds of millions of years. Different speeds, but the same calm persistence. Nothing is trying to finish. Nothing is trying to arrive. Rotation is not a race. It is a state. And when you begin to see it that way, something shifts in how you experience it. Motion stops feeling urgent. It becomes steady, because rotation doesn't accelerate toward an end. It sustains itself. It continues because the conditions allow it to continue, because the balance holds, because angular momentum remains. And that continuity creates a kind of quiet stability. Even in a universe that is constantly moving, there is no sense of panic, no sense of disorder, just motion that flows naturally from one moment to the next. And you are part of that same flow. Your thoughts may speed up or slow down. Your day may feel busy or calm, but beneath that, you are still carried by something steady. The rotation of the Earth has not changed. The orbit around the Sun continues. The galaxy still turns. There is a deeper rhythm underneath everything you experience, and you don't have to match it perfectly. You don't have to think about it constantly. Just knowing it's there can be enough, because in a world that sometimes feels fast, unpredictable, or overwhelming, it helps to remember that the universe itself moves in a way that is anything but rushed. It spins, it repeats, it continues, and there is no hurry in any of it. After everything you've followed, everything you've imagined, everything you've allowed to settle, one final idea begins to emerge. Everything is already balanced, not perfectly in every moment, not in a way that prevents change or transformation, but balanced in a deeper sense, balanced through conservation, balanced through motion, balanced through the quiet persistence of physical laws. Because every time something spins, something else responds. Every time angular momentum shifts, it is accounted for. Every time motion changes form, the total remains the same. So even when systems evolve, even when things appear chaotic or complex, there is an underlying order that does not break. A planet may slow its rotation, but its moon moves farther away. A star may lose angular momentum, but its wind carries it outward. A galaxy may collide, but the motion redistributes, not disappears. Nothing is lost. It is only transformed. And this is what creates stability in a moving universe. Not the absence of change, but the presence of balance within change. So when you think about everything spinning, It's not something that needs to be controlled or understood in detail. It's something that already works, already holds together, already continues without effort from you. And maybe that's the most calming part of all. You are not responsible for keeping the universe in motion. You are not responsible for maintaining its balance. It is already doing that perfectly, quietly, continuously, and you are simply part of it, moving within it, existing within it, without needing to hold anything together yourself. If everything you've heard could be reduced to one simple idea, one quiet sentence that holds the entire journey, it might be this: the universe moves, and in that motion, it finds its shape. Rotation is just one expression of that movement, but it is one of the most visible, one of the most consistent, one of the most revealing. It shows you that motion is not random. It organizes, it shapes, it sustains. From the smallest particles to the largest galaxies, the same principle repeats. Motion becomes structure when it turns, and once it turns, it continues. Because angular momentum is conserved, because symmetry demands it, because the laws of physics allow no alternative. So the reason everything spins is not a single event, not a single cause. It is the natural outcome of a universe where motion exists, where symmetry holds, and where conservation governs everything. And that idea does not need to be held tightly. It can rest lightly in your mind, like a quiet understanding that doesn't need to be repeated or analyzed, because once you see it, you don't need to search for it again. It is already there, in every rotation, in every orbit, in every slow turning system you can imagine, and even in stillness, it remains. Now, there's nothing left to explain, no more systems to explore, no more layers to uncover, only the quiet understanding that everything continues, whether you think about it or not. The earth is still spinning beneath you. The night sky is still moving above you. The galaxy is still turning, slowly, endlessly, and all of it will continue, long after this moment fades. So you don't need to follow it anymore. You don't need to track it. You don't need to understand it further. You can simply let it be. Let the motion continue on its own while you rest within it. Because even though everything is moving, you are allowed to feel still. Even though the universe never stops spinning, you can let your thoughts slow down. There is nothing you need to do, nothing you need to solve. Everything is already in motion. Everything is already balanced, and you are already part of it. So as the rotation continues, quietly, endlessly, you can begin to drift, not away from it, but deeper into it, into a place where motion and stillness are no longer separate, where everything flows and nothing needs to be held onto. Just a universe that spins and a moment that gently fades. Before you drift completely into rest, just remember this: the universe is still gently moving, still spinning, still holding everything together in quiet balance, and you don't have to follow it anymore. You've already traveled from the smallest particles to the largest galaxies, from the beginning of motion to the reason it never stops. And now there is nothing left to figure out, only something to feel. So as you close your eyes tonight, let that thought stay softly with you, that you are not alone in the stillness. You are part of something vast, something steady, something that has been moving in harmony for billions of years. The earth beneath you continues its slow rotation. The sky above continues its silent motion, and everything around you remains in perfect balance, without needing anything from you. If this journey helped your mind slow down, even just a little, you can gently like the video so it can find others who need the same quiet space. And if you'd like to return to this feeling again, you can subscribe and come back anytime. For now, there's nothing left to do, nothing left to understand. Just let the motion continue while you rest inside it. Good night, and welcome back to stillness within a spinning universe.